In this subsection, we're going to talk about something called sampling with replacement and something called sampling without replacement. But we're going to illustrate this through the use of an example. So let's start with that example. Here it says, a bag contains 15 balls, 10 black balls and 5 white balls. We draw 3 balls out of the bag. What is the probability that all 3 balls are black? A, if we put the ball back into the bag after it's chosen, so we pick one out, look at it, is it black or white, put it back in, pick another one out, is it black or white, put it back in. Or B, if we do not put each ball back into the bag after it's chosen. So we pick one out, look if it's white or black, then put it over somewhere else, and then pick one out of what's left in the bag. So these are two slightly different problems. Let's start with problem A. So again, omega is the set of sequences of white or black balls that can be pulled out of the bag. Sequence of 3 white or black balls. So, how many elements are there in omega? Well, there are 15 balls in the bag, right? The 10 black and the 5 white. So there are 15 choices for the first ball, and 15 choices for the second ball, and 15 choices for the third. And by our multiplication principle, which we now know and love, it's going to be 15 times 15 times 15. So here we have the number of elements in omega is 15 cubed, which is apparently 3,375. And our event A that we're interested in is the event that all 3 are black. And again here, number of elements of A are, well, there are 10 black choices that could be the first ball, and 10 for the second and 10 for the third. So this is 10 cubed, which I happen to know is 1,000. So, probability of A, as we know for classical probability, it's the number of outcomes in A over the number of outcomes in omega, which is 1,000 over 3,375, which is apparently about 30%. Okay, now let's look at part B. Remember that part B is when we take the ball out of the bag, look at what colour it is, and then put it over there, and then take another ball out of what's left in the bag. So, how many elements are there in omega this time? Well, here there are 15 choices for the first ball. But then, once that ball's been taken out, there are only 14 choices left for the next ball. And once that ball's been taken out, there's only 13 choices left for the final ball. So we get 15 times 14 times 13, which is the smaller number, 2,730. So note that here what we got was this declining multiple, 15 times 14 times 13. We're multiplying numbers where the numbers get smaller each time. Similarly, for our set A, that we get a black ball, then a black ball, then a black ball, well, there are 10 choices for the black ball first time round. But then once we've picked a black ball and taken it out, there's only 9 black balls left the next time, and only 8 for the next time. And by the multiplication principle, we multiply those together. So that gives us 10 times 9 times 8. 9 times 8 is 72, so this is 720. And again, we have one of these declining multiplications, 10 times 9 times 8. So again, here, probability of A equals number of elements in A, the number of elements in omega, 720 out of 2,730, which is apparently a bit smaller. That's about 26%. So we got different answers depending on whether or not we put the balls back into the bag after looking at them. So the distinction between these two things is known as sampling with replacement, when you put the ball back into the bag, and sampling without replacement, where you don't put the ball back in the bag, put it over there. So what are the general rules that we saw examples of there? So we saw that when sampling k objects from n. So you've got n total objects and you want to pick k of them. Then if you do that with replacement, that is, you pick one of the n objects and put it back, and pick one of the n objects and put it back, and do that k times, then you have k choices each time. Right, so you get n to the k, which is n times n times n, k times. I know you all know what n to the k is, but there you go. Whereas on the other hand, if we do it without replacement, then we get n choices the first time, but then the next time there's one fewer objects to pick one from, so we only get n minus 1 the next time, and then n minus 2 the next time, n minus 3 the fourth time, n minus 4 the fifth time, up until the kth time, where that's n minus k plus 1. Just to confirm, because the first one is like n minus 0, the last one is n minus k plus 1, but that still means that there are k terms in the multiplication. And we will call that in this course n to the k, but underline the k. So n to the k normal just means n times n times n k times, but n to the k underline means we get this lowering number, n minus 1, n minus 2, that we multiply together k of those terms, ending with n minus k plus 1. So this number here, n underline k, where we multiply gradually smaller and smaller numbers, I call that the falling factorial. Falling because each number we multiply is getting a little bit smaller. Another term you might see in books or on the internet, permutation number. It's also the case that the world hasn't really decided on notations for this thing. So I use n to the k with the k underlined. But you may also, again, in books or the internet, see n in brackets with a k downstairs. And you might see things with a p for permutation, like pnk, or sometimes p with an kind of n at the top left and a k at the bottom right. Those are other formulas you might see. But this is the difference between whether we're sampling objects with replacement, in which case it's n times n, or sampling with them without replacement, in which case we get this falling factorial where each number is smaller. We denote that n to the k underline. And that will be an important idea when we're counting up objects to find a classical probability.